Welcome, this is Professor Ridge, and today's lesson 6.7, Exponential and Logarithmic Models. Our first learning objective, model exponential growth and decay. Alright, let's review some characteristics of the exponential function y equals a sub 0 e to the kt. So notice that both of the functions, whether it's what we call exponential growth or exponential decay, is they're one-to-one functions. We have a horizontal asymptote on the x-axis, y equals 0. The domain is all real numbers, negative infinity to infinity. So remember the x values. So you can put in any x value, you'll get a y value. The range is just the positive real numbers. So from 0 to infinity for either one. X-intercepts, right, and there is none, right? It doesn't hit the x-axis. It's a asymptote. And then the y-intercept is 0, a sub 0, which is the initial value, right? A sub 0. If k is a positive number, it's exponential growth, and it's an increasing function. And if k is a negative number, that's exponential decay. And it's decreasing. Okay, example 1, graphing exponential growth. A population of bacteria doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. So the x-axis is going to be time. So time. And then these are in hours. And then this would be the number of bacteria for y. And we started out with 10. Every hour it doubles, so it goes to 20, 40, 80, 160, and then 320, which is off the chart here. So you can see this curve is that exponential growth curve. Okay, so now if we want to figure out the equation of that, let's see here. So we know that we have our basic y equals a sub 0 e to the kt, and let's put in a couple points here. So we know a sub 0 is 10, so we'll start with that, and then kt. So now let's put in 120 in here. So if we put in 20 e to the k times 1. So we're going to divide by 10. So 2 equals e to the k. Now we do ln of both sides. Remember, ln and e are inverses, so they cancel each other out. We get k all by itself. And that's ln of 2. So this equation is going to be y equals a sub 0 is 10, e to the ln of 2 times x. Okay, half-life. We now turn to exponential decay. One of the common terms associated with exponential decay, as stated above, is half-life, the length of time it takes an exponentially decaying quantity to decrease to half its original amount. Every radioactive isotope has a half-life, and the process describing the exponential decay of an isotope is called radioactive decay. To find the half-life of a function describing exponential decay, solve the following equation. So if you remember from the last section, we did a half-life problem, and I said, well, I tend to do it a different way. This is the way I would do it, the way it process here. So if we start out with our exponential function, growth or decay, right? It's a sub 0 e to the kt. I usually use r, but that's okay. R for rate. Anyway, so if we want half-life, then we want the amount at time t to be half the original amount. Remember, a sub 0 is the original amount. So we're going to solve this equation for t to find the half-life. And the technique is we want to get e to the power by itself. So we're going to divide both sides by a sub 0. A sub 0. So the a sub 0's cancel. I don't know what's going on with my pen. 1/2 equals e to the, those cancel, kt. Now we're going to do ln of both sides. Ln of and e cancel each other out. So we get kt equals ln of 1/2. Now, from here, we're going to divide both sides by k to get to, so t equals ln of 1/2 divided by k. Now the book, to make it easier, they do ln of 1/2 is the same thing as negative ln of 2. Me personally, I just leave it like this. I'm not going to do that. To me, it's easier to memorize this because if I want half-life, it's ln of 1/2. And when I do something that's exponential growth and I want to know the doubling time, double is twice, so ln of 2. So for me personally, this is easier to remember. But just note that ln of 1/2 is equal to negative ln of 2. And you can test that out on a calculator. Okay, example 2. Finding the function describes radioactive decay. The half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time t. Okay, so we want to basically find a function for our amount that's left remaining as a function of time. So we start with our basic formula for growth or decay. We know the half-life, so we're going to do 1/2 of our original amount. We don't care what that original amount is because it's going to cancel out. E to the k, and now the time is 5,730. So we're going to solve this for k, so we can plug the k in here and write this as a function of time. Okay, so we need to figure out what k is. So let's see here. So we divide both sides by a sub 0. And then we're going to do ln of both sides. Okay, so the ln and e cancel each other out. I'm going to rewrite this as 5,730 k equals ln of 1/2, and then divide by 5,730. And if you punch this in the calculator, you can approximate it. So k is equal to that number, ln of 1/2. Or you can write 0.5 of 5,730. So our equation would be a sub 0 for our initial amount, e to the ln of 0.5 divided by 5,730, sorry, times t. And that's our equation. And again, if you want to approximate this, you can get a decimal. You want to go take a whole bunch of places, so sometimes it's easier just to leave it like this for the exact answer and just type that in your calculator. Okay, I want to point out too that we could have saved some time, and if you go back to this and solve this generically for k, so if you want to know the rate given time, we could have gone back to this process here, and instead of dividing by k, we divide by t, and we get this formula. And remember, negative ln 2, same thing as ln 1/2. So I could have just jumped to k equals ln of 1/2, which is the same thing as 0.5, divided by the time. So I could have skipped all this work and just put in the 5730 to get, and then I can get a decimal number. Right. In fact, let's do that just so we know. Okay, so we could see it's negative 1.209, 4 decimal places. So it's negative 0.0001, I think it was 29, right? 209. Oh, so that would round up to 9, so that would be 10. So 1, 2, 1. If we want to go out 6 places. 1, 2, 1. Okay. So again, we could have saved some work here and just used this shortcut here. So we can use this for radiocarbon dating. The formula for radioactive decay is important in radiocarbon dating, which is used to calculate the approximate date a plant or animal died. Radiocarbon dating was discovered in 1949 by Willard Libby, who won a Nobel Prize for his discovery. It compares the difference between the ratio of two isotopes of carbon in an organic artifact or fossil to the ratio of those two isotopes in the air. It is believed to be accurate to within about 1% error for plants or animals that died within the last 60,000 years. Okay, so carbon-14 is a radioactive isotope of carbon that has a half-life of 5,730 years. It occurs in small quantities in the carbon dioxide in the air we breathe. Most of the carbon on Earth is carbon-12, which has an atomic weight of 12 and is not radioactive, so it doesn't decay. Scientists have determined the ratio of carbon-14 to carbon-12 in the air for the last 60,000 years, using tree rings and other organic samples of known dates, although ratio has changed slightly over the centuries. As long as a plant or animal is alive, the ratio of the two isotopes in its body is close to the ratio in the atmosphere. When it dies, carbon-14 in the body decays and is not replaced. By comparing the ratio of the carbon-14 and carbon-12 in a decaying sample to the known ratio in the atmosphere, the date the plant and the animal died can be approximated. Since the half-life of carbon-14 is 5,730 years, the formula for the amount of carbon-14 remaining after T years is A is about A sub 0 E to the ln 0.5 divided by 5730, right? T. So this formula that we just did, they solve it. So A is going to be the amount of carbon-14 remaining. A sub 0 is the amount of carbon-14 when the plant or animal began decaying. Okay, and then we just solve it just like we did before. And we'll just jump down to here. So to find the age object, we solve this equation for T. T equals ln A, the ratio of A to A sub 0. So again, A is the amount of carbon-14 remaining divided by the amount of carbon-14 when the plant began decaying. So that's what we want to solve for there. Or I should say, this is what is left in the sample that you have, and you can analyze it. And then you get this ratio plug it in here, and that we're solving for t, so that way we know when it began decaying. Alright, let's try example 3 here. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? Again, so we're going to plug in the ratio 20%, so 20% of the original, or I just do 0.2, and then just type this in our calculator, and then we can approximate it that. Okay, so it is 13,301 years old. 13,301 set to the nearest year. Calculating doubling time. For decaying quantities, we determine how long it took for half of a substance to decay. For growing quantities, we might want to find out how long it takes the quantity to double. As mentioned above, the time it takes for a quantity to double is called the doubling time. So again, this is why I like to use 1/2 for the half-life and 2 for doubling time, and then I kind of keep these formulas straight. They're the same. So if you see, where was it? Right here. Again, the book uses minus ln of 2, which is the same thing as ln 1/2. But this would be for half-life, so ln 1/2 divided by k. And then for doubling time, ln of 2 divided by k. And it's the same thing, same process. So I'll let you read that on your own. Example 4, finding a function that describes exponential growth. According to Moore's law, the doubling time for the number of transistors that can be put on a computer chip is approximately 2 years. Give a function that describes this behavior. So we're going to double every 2 years. So if we start out with the formula, a sub 0, e to the kt, and our doubling time is going to be, so we can solve this, or let's use the shortcut. Remember, to find k is equal to ln of 2 for doubling divided by time. See, this is the two formulas. You can interchange those. So if you know the doubling time and you want to know the rate, you just do ln of 2 divided by time. If you know the rate, you can figure out the doubling time by doing ln 2 divided by k. So basically, you can just do, you don't have to do this whole formula. So if the doubling time is 2, ln of 2, like that. So our exact answer will be a sub 0 e to the ln of 2 over 2 t. Now if you want to get an approximate number for that, let's see what that would be. Okay, so that is about 0.693. If you want to do one more place, it's 1/4, or a couple more places, 147. Okay, so again, depending on what you're doing, sometimes you like more accurate, so you just leave it ln of 2 divided by 2. Okay, on to our next learning objective. Use Newton's law of cooling. Okay, exponential decay can also be applied to temperatures. When a hot object is left in a surrounding air that is at a lower temperature, the object's temperature will decrease exponentially, leveling off as it approaches the surrounding air temperature. On a graph of the temperature function, the leveling off will correspond to the horizontal asymptote at the temperature of the surrounding air. Unless the room temperature is 0, this will correspond to a vertical shift of the generic exponential decay function. This translation leads to Newton's law of cooling, the scientific formula for temperature as a function of time as an object's temperature is equalized with the ambient temperature. So here's the formula. So capital T of T. So temperature as a function of time equals A e to the kt plus T sub s. Okay, so the A is the initial, here they rewrote it as capital A, where that's the A is the difference between the initial temperature of the object and the surroundings. So that's the initial difference. And then T sub S is the temperature, let's see, the surrounding air temperature, right? So that's what that sub S is. And let's see, the temperature of the object is the T. So this is T as a function of this capital T. This is the temperature of the object as a function of time. So that's the difference between the object in the air. And then the little t is time. And then the capital T sub S is the temperature of the surrounding air. All right, how to, given a set of conditions, apply Newton's law of cooling. Set T sub S equal to the y coordinate of the horizontal asymptote, usually the air temperature. Substitute the given values into the continuous growth formula, given here. Define the parameters A and K. Substitute in the desired time to find the temperature, or desired temperature to find the time. Example 5. Using Newton's law of cooling, a cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed into a 35 degree Fahrenheit refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. If we must wait until the cheesecake has cooled to 70 degrees Fahrenheit before we eat it, how long will we have to wait? This is my kind of question, right? I want some cheesecake here. All right, so let's see. All right, let's start with, we know the surrounding air temperature is 35. So let's see, A e to the kt plus 35. And then let's see, we know that let's see, cheesecake's taken out. So we got 2 points here. Time is 0, it's 165. And then time is 10 minutes, it's 150. So let's plug in those numbers to figure out some of these variables. So if we plug in 0, the temperature is 165. So A e to the 0 plus 35. So anything to the 0 is 1. And then we're going to subtract 35 from both sides. So this is 1 and then times A. So that tells us A is 130. Okay. So now we have, our formula is T sub T of T is equal to A, which is 130. So that's the difference in the surrounding temperature, right? We just subtract those, so we didn't actually have to do it that way, but that's okay. E to the kt plus 35. Now we want to figure out K, so we're going to plug in one more, this value. So 150 equals 130. E to the kt is 10 plus 35. So we're going to subtract 35, so that's 115. I'm just going to rearrange that as 10k. Then I'm going to divide by 130. So now I have, do I want to leave this as a fraction? Yeah, we'll leave it that way to get more exact answers. Then we do ln in front of both sides, 115 over 130 equals, the ln and e cancel each other. So if you wanted to save a step there, right, you're just going to write 10k here. And then we're going to divide by 10. So k is ln of 115 over 130 divided by 10. Okay. All right, so now we want to solve when is it going to be. Okay, so that's kind of our work to get to k. So t of t is a, which is 130, e to that number. I'm just going to leave it in as, well, I guess I'll go ahead and write it. 115 over 30, 130, sorry, over 10 times k, and we want to know, let's see, oh no, t, then plus 35. So we want this to be 70, and we're solving for t. I'm just going to leave this as k for right now, and then I'll plug that in. Just not real fond of writing that number. Okay, so I'm going to subtract 35 from both sides. So that's 35. And then I'm going to divide by 130. So hopefully you're getting used to these steps. Then I'm going to divide by, or I'm going to do ln to both sides. So ln and e cancel each other, and then we get the k, which is this number. So I'm going to go ahead and write it. So ln of 115 over 130 divided by 10 times t, which we're solving for. Now we're going to divide by this number here. So t equals, and I'm flipping it, so this number on top, ln of 35 over 130 divided by ln divided by ln of 115 over 130 over 10. And punch that in my calculator. So that's going to be, and we want it, we'll probably round it to the nearest minute or so. Okay, so you can see we get 107 minutes or so, which is what, 1 hour, 47 minutes? Okay, so not too bad. Less than 2 hours, you'll be having some cheesecake. Okay, so our next learning objective, use logistics growth models. The logistics growth model is approximately exponential at first, but then it has a reduced rate of growth as the output approaches the model's upper bound, called the carrying capacity. For constants A, B, and C, the logistic growth of a population over time is represented by the model f of t equals c over 1 plus a times e to the negative bt. Okay, so c is called the carrying capacity. And then, let's see, the graph figure 6 shows how the growth rate changes over time. So see, it starts out, looks like exponential, and then at some point it starts tapering off, and we don't want to go beyond the carrying capacity of whatever the growth model is for. All right, so here's the growth model again. C over 1 plus A is the initial value. Because if you put in time as 0, this whole part becomes e to the 0 is 1, so this whole part goes away and it'll be 1 plus A. So you can figure that out. C is the carrying capacity or limiting value, sometimes we call it that. And B is the constant determined by the rate of growth. Okay? Example 6, using the logistic growth model, an influenza epidemic spreads throughout a population rapidly at a rate that depends on two factors. The more people who have the flu, the more rapidly it spreads. And also, the more unaffected people there are, the more rapidly it spreads. These two factors make the logistic model a good one to study the spread of communicable diseases. And clearly, there is a maximum value for the number of people infected. That's the entire population. So that would be the limiting factor. For example, at time t equals 0, there's one person community of 1,000 people who has the flu. So in that community, at most, 1,000 people can have the flu. Researchers find that this particular strain of the flu, the logistic growth constant is B equals 0.6030. Estimate the number of people in this community who will have had this flu after 10 days. Predict how many people in the community will have the flu after a long period of time has passed. Okay, so let's start out with our logistic model. So f of t is equal to c over 1 plus a e to the negative bt. We're going to put in 1,000 for the carrying capacity. So f of t is equal to 1,000. Let's see. C, we know that from, let's back up here, C over 1 plus A is the initial value. So remember, the initial value was one person was 1. So C over 1 plus A is equal to 1. So 1,000 over 1 plus A equals 1. Okay, we can just cross multiply. Think of it that way. So 1,000 equals 1 plus A, just if you multiply that way. And then, so that must be A is 999. 1 plus 999. E to the negative B. B is 0.6030, and then T. All right, so estimate the number of people the community have after 10 days. So we're going to put 10 in here. F of 10 is 1,000 over 1 plus 999 e to the negative 0.6030 times 10. Okay, and we're just going to punch this in our calculator. And that is going to get us, okay, so again, just punch it in the calculator, 1,000 divided by 1.1 plus 999 e to the negative 0.6030 times 10, and we get 293.8. We'll just round it to the nearest person. 294 people. Have the flu after 10 days. Let's see. How many people in this community will have the flu after a long period of time has passed? So it's going to get close to 1,000, right? This is approaching. So remember the curves, they look like this up to that carrying capacity. Okay, so let's see. So I'm going to put in y equals 1,000 for that carrying capacity. So I just changed the one that I just did, put an X there, and that gave me the graph. And let's zoom out let me change the y-axis to be let's do 1,000 here. Do 1,000. Okay, and you can see, oh, so it's not taking that long. So about 21 days actually is when it's going to hit. Now it doesn't actually equal 1,000, right? It's just the way it's rounding. So theoretically it's not going to be 1,000. It's going to approach it and get as close as you can get to it. So look, it only takes about 21 days for the whole population, virtually the whole population, to get the flu. Okay, choose an appropriate model for data. That's our next learning objective. Okay, choosing a mathematical model. Does a linear, exponential, logarithmic, or logistics model best fit the values listed in Table 1? Find the model. Use a graph to check your choice. So let's look at Desmos. Okay, so we can add a table, and then we can just input the values that they gave us. Let's see how they do it. 1, 2, 3. Okay, so watch this. So I have my x's are going to be 1, 2, and then it just follows the pattern. I think we went to 9. And then we can put in 0, 0, and see it plots it for us. 1, 0. 1.386. Then we do 2.197, 2.773, 3.219, 3.584, and then, okay, you can see that's not going to make a straight line, so I went ahead and put all the rest of them in there. So let me do something real quick. So here we go. So again, clearly, right, it's not going to make a straight line. So if I try to connect these two dots, you can see it's not going to make a line. So a line doesn't work. Exponential function doesn't go that way. We know exponential function looks like, or at least you should know, an exponential function looks like this. A logistics model looks like this, where it starts out and then levels off. And this looks more like a logarithmic function, right? Logarithmic is the inverse of an exponential. So that looks like a log function. Okay, so let's write down a basic log function. So let's start with y equals a natural log of bx. And let's put in some points. So we have 1, 0. So if we plug in 1, 0, so y is 0, x is 1, so 1 times b is b, and then you can divide by a, so we got 0 equals ln of b, and then what does that give us? A. So if a is 0, then all the outputs would be 0, and log of b equals 0, so b has to be 1, right? So this is a property. The log, it doesn't matter what the base is, of any number I lost my train of thought there for a second. So log, we did b, but I don't want to use this b. So log base a, I should put x. So a to the 0 is 1. So this number has to be 1. So b is 1. So b equals 1. Okay. So anyway, let's get rid of all this stuff so I can use it. Now, so now we know b is 1. So we got log equals a ln of x. And then now we got to figure out a. So let's pick another point. How about, I don't know, we can pick any of these. How about 8, 4.1? Or we can do the 9. Okay, so 9 is 4.394 equals a ln of 9. So then divide both sides by ln of 9. And punch that in our calculator. Okay, so we get 1.9997. So we'll round it to 2. Close enough. So we're going to say that is about 2. So a is about 2. So now we have our formula. Y equals log. 2 log, sorry. 2 log of x. And that will fit. And then let's check it. So we'll graph that on Desmos and see if it kind of hits those points that we just did. So y equals 2 natural log of x. Oh, did I write log instead of ln? And yeah, you can see that these are hitting those points. Now, is it exact? I don't know, but pretty close, right? So it's going through them. Yeah, I wrote log. This is log base 10, which is not the right answer. So let me erase that. Good thing I looked at the graph. So 2, we did ln. So 2 ln natural log. So that's base e. Okay, let's look at the next problem. And on to our last learning objective, express an exponential model in base e. Okay, how to, given a model with the form y equals ab to the x, change it to the form y equals a sub 0 e to the kx. Rewrite y equals abx as y equals a e to the ln bx. So again, remember here, e, ln, those are inverses. So those would cancel and we just get b to the x. So you can see that that's the same. So we can use that rule in both directions. Okay, use the power rule of logarithms to rewrite. So we're going to take this and bring it out as a, let's see, we're going to take this x and bring it out as a power. So a e the x times ln b. So we brought that x out in front of the ln. And then that equals, oh, they just rearranged it, right, because it's multiplication. And then, let's see, note that a is equal to a sub 0 and k is equal to ln of b. In the equation, y equals a sub 0 e to the kx. So basically, if you want to rewrite base b to e to the kx, you're just going to do ln of b, and that'll become your k. Right? Okay, so let's try this. So change the function y equals 2.5 times 3.1 to the x so that the same function is written in the form y equals a sub 0 e to the kx. So this a, which is 2.5, is going to be a sub 0. So those are the same. Okay, so we get y equals 2.5 e. Now the k, this is the b. The b is going to be, or k is going to be ln of b. So K will be ln of 3.1. So if we punch that into our calculator, so let's see, oops, ln of 3.1, so it's 1.131. We'll go out 3 places. That's good. So 1.3, oh, I'm sorry, 1.131, and then x, and that's it. We're done. Okay, I take that back. It looks like the book, we want to keep this the exact number, so we're going to write this as y equals, so this is approximate, right? So we want to leave it the ln of 3.1 times x. So that's going to be our answer. And if we graph this on Desmos and graph this one on the original one, you'll see they're the exact same graph. This one will be off just a tiny bit because we rounded, so the book's just leaving it in this form. Okay, so that brings us to the end of the lesson. And again, practice, practice, practice. Go to the end of the section, do the exercise set there, do all the odds, and as many of the evens if you have time. All right, have a great day, and I'll see you next time.